Let's discuss degeneracy of Landau levels. A huge density of states of a two-dimensional electron gas needs to be squeezed to narrow Landau levels. So each Landau level will have enormous degeneracy. And to quantify it, let's use our similar trick to finding density of states in a 2D material. So we take a sample with dimensions of Ly, Lx, and it will have a density of states of some n electrons or so per area. But let's see what happens in the magnetic field. So when you have a magnetic field, your Landau levels are, so wave functions are the stripes, so the electrons will be found in some narrow regions along the y direction. So wave functions are stripes. And they will be separated by a delta x naught, this offset. So the separation is delta x naught. Now we can do the analysis. So the delta x naught is, we take from this equation, so hk over EB, so h bar over EB times delta k. So our delta k is 2 pi over Ly. That's the way, so we basically cut the sample into many pieces, and then you have the separation between each state, because those are still fermions, so they will each occupy individual levels. So our delta k is 2 pi over Ly. Similarly, how we derive the density of states for a normal electron gas in a free particle model for 2D, 1D, or 3D, or so on. So that is now h bar over EB 2 pi over Ly, or because it's h bar 2 pi, so this is h over EB Ly. And our degeneracy is, so the density of states, degeneracy, so not degeneracy, is the Lx divided by delta x naught. We are simply counting how many of those stripes we have in our sample. So that's basically counting them. Now you can rewrite this Lx Ly EB over h. So that's the result for a carrier density, or for the density of states, or in other words for degeneracy of the Landau level. And we use it usually per unit area. For A it will be n is a naught over Lx Ly, and then it's just EB over h. It's quite an important result. So the degeneracy of Landau levels only depends on the fundamental constants and the magnetic field. So there's no parameters related to the sample. Yeah. Let me show it graphically. So this is energy, and this is our density of states. And in a 2D gas, two-dimensional electron gas, if you are staying in the same subband, you don't move it out of it, so it's just a constant. And now, if you have a magnetic field, what happens to the degeneracy? Energy, G of E. You will have instead a set of spikes, where you have like no density of states, then there will be a spike, no density of states, spike, no density of states, spike, and so on. And each spike of each of those spikes corresponds to the Landau levels. And then somewhere in the system you will have a Fermi level. So let me use a different color. So somewhere here is a Fermi level, for example. So if the Fermi level is in Landau level, it only can happen when the condition for this position of the energy level is satisfied. So it has to be, EF must be equal n plus 1/2 h bar EB over m. That's from our eigenvalues. That's this one. So in the middle of Landau level, we can relate this the index of Landau level, this n here. This is a Landau level index, and it can be related with electron density. So the carrier density, or n sample. So density, I'm just using this subscript to differentiate it from the index of Landau levels. Is 2, because of spin, times the degeneracy, which is just this part here, degeneracy, times the index of Landau levels. So you basically count how many of those states you feel as you move with your Fermi level. If you start feeling these electrons, you feel each of those degeneracies, so you multiply by the degeneracy, and then you multiply by this by the index, by the Landau level index, which is n plus 1/2 in our case, which can be rewritten as 2 EB over H n plus 1/2. And we ignore Zeeman effect. I'm using red. So because the Zeeman effect, what it would do, so if you have a Landau level, it will then split it into spin up and spin down state. And yeah, so the degeneracy will be lifted. You will have two different Landau levels with the different spins there. So we're ignoring it in this description. Sometimes there is a quantity. You can see here there is index 2, n, 1. Sometimes there is a so-called filling factor. Filling factor is usually denoted as nu and defined as 2n plus 1. So in this case, if you use a filling factor, then the carrier density in the sample is nu times n, or nu times EB over H. And this allows you to have a relation between the carrier density, filling factor, or Landau level index, and the magnetic field.